Hello everyone, welcome to Drawing Hub. This is Sanjana, and in this video we'll be continuing with the rest of distributed computing part 4 of module 1. In the previous sessions we have already discussed about the basics of distributed computing, the features, motivation, what middleware is, the primitives and all those things. If you want to get more clarification on those topics, please visit and watch my previous videos. And in this video, we'll be continuing with the 4 versions of send primitive. We already have learned what synchronous, asynchronous, blocking, non-blocking is. I'll just give you a recap. If the sender wait for the receiver, that is synchronous. If it does not wait for the receiver, it is asynchronous. If the function returns immediately, it is non-blocking. If the function does not return immediately, that is blocking. And with that, we have 4 combinations, that is synchronous blocking, synchronous non-blocking, asynchronous blocking, asynchronous non-blocking. Okay, this is we will be having 3 timelines. One is process execution, one is user buffer, and one is kernel buffer in the figures. Okay, then we have blocking synchronous send. This is actually the slowest method. What happens here is there is a send data. You can just have a look at the figure. There is process I, which is the one processor which sends the data, and the process J is one which receives the data. Okay, S over here is send primitive, R is receive primitive, SC is processing for send completes, the send is complete, and RC is processing for receive completes, it denotes. Then we have buffer and all, and the shaded block, as you can see, that is the duration of how much time it takes to copy the data from or to user buffer. And the one without the shaded, the unshaded block, is the duration in which the process issuing send or receive primitive is blocked. Okay, then you also have P and W, which we'll be discussing in when it will be shown in the figure. What happens here is it sends the data. Which one? The process I sends the data, that is copied, and it is moved to the network. The receiver receives it, and only after the acknowledges is sent, the sender will continue. Why? Because it is a blocking synchronous send. Blocking and synchronous. What here, the sender waits for everything. Only after the receiver has received the message and acknowledged, only then the sender will continue its working. Similarly, we will have blocking receive also. The receive call blocks until the data expected arrives and is written in specified user buffer. Then we have non-blocking synchronous send. Non-blocking synchronous send, this sender, the control will be given back immediately because it is non-blocking. It will send and it will continue working. It is not going to wait. But the operating system will still wait in the background until the receiver receives the message, and when it completes, a handle is marked as completed. This work is completed, and the program can check this later, or it can call the wait function to block until it's done. So this handle is something which is like a tracking number for a courier. When you send a courier and all, you can track where the courier has reached. So that is something which we can relate to handle. That is about non-blocking synchronous send. Here P is the completion of previously initiated non-blocking operation, and W is the process may issue wait to check completion of non-blocking operation. The control will return back once the process is invoked. Similarly, you will have non-blocking receive also. Here the receive call will cause the kernel to register the call and return the handle. The user process can check for completion of non-blocking receive by invoking the wait operation on the returned handle. Okay, this is the figure for both blocking synchronous send, blocking receive, and non-blocking synchronous send and non-blocking receive. Then we have blocking asynchronous send. Blocking asynchronous send. What does asynchronous mean? It is not going to wait till the receiver sends the acknowledge. The sender waits only until the data has been copied out of its own buffer. It will wait until the control is returned back. It does not wait for the receiver to receive the message. So once the copy is complete, it will continue doing its work. That is blocking asynchronous send. Then non-blocking asynchronous send. This is actually the fastest and most widely used form of send. It will send and it will continue immediately. The communication will happen in the background. The sender keeps working while the message travels through the network. If it wants to reuse the send buffer safely, it later checks the handle or uses wait function. And this method gives the highest parallelism. Now, why we need the wait function is because suppose you send a large file. The operating system will say, don't worry, I'll send it, and you continue doing other work. Later, before reusing the same memory buffer, you need to know whether that send has finished or not. So you will ask using this wait function. If the communication is complete, then the wait function returns immediately. Otherwise, it will block until the operation finishes. That is the use of wait function. Then again here also you have blocking asynchronous send and non-blocking asynchronous send figures. Comparison. Synchronous send is very easy to use from a programmer's perspective, because when we see it, we'll feel that all the communication is happening very fast, but it is not actually. And the synchronous send has lower efficiency within the process PI, that is the sending process. It has lower efficiency. In non-blocking asynchronous send, it is useful when we are using large data item, because everything will be happening in parallel. With the completion of send, everything happens parallelly, so that is useful over there. Whereas in non-blocking synchronous send also, this can also avoid potentially large delays, but still there are some certain disadvantages. And for non-blocking calls, the programmers will find it very hectic, because that person, the programmer, will have to keep track of the completion of such process. Only then they can reuse the user buffer. Then we have processor synchrony. Processor synchrony, we can start with an example. Imagine your teacher says, everyone solve question number 1, and everyone will start solving question number 1. No one will start question 2 until everyone has finished question 1. So what happens here is everyone finishes one step together. Only when they complete it, they will move to the next step. This is called synchronization. Processor synchrony means all processor execute in lockstep with synchronized clock. But practically thinking, is this possible? No, because we have already learned distributed systems do not have common clock, right? They do not have common clock. They have different processors. They have different speed. So perfect synchronization is not possible. It is impossible. Then what do distributed system do? Instead of synchronizing every instruction, they synchronize large blocks of works called step. We'll take another example. Let us say there is computer number 1. Computer number 1 will finish task A. Okay, it will finish task A and it will wait. Then there is computer number 2. It will also finish task A and it will wait. And there is computer number 3. This will also finish task A and it will wait. Only when everyone finishes task A will they start with task B. And this waiting point is called barrier. Okay, this waiting point is called barrier. Only after everyone reach a checkpoint, only after everyone arrives at it, the next task is being done. That is called barrier synchronization. So processor synchrony means processors execute in synchronized steps. Since perfect clock synchronization is impossible in distributed system, barrier synchronization is used to ensure that all processors complete one step before beginning the next. That is processor synchrony. Then we have libraries and standards. In libraries and standards, suppose you want to send a message. Will you write thousands of lines of networking code? No. Instead, we use a library. Just like in programming in C, you can call a print function or a scan function. What is this printf and scanf function? They are library functions. So Similarly, in distributed computing, they also have communication libraries like message passing interface. MPI is message passing interface. This MPI is one of the most important one, which is mainly used in supercomputers, scientific computing, parallel computing and all. The message passing interface, this MPI provide functions like MPI send function, MPI receive function. Instead of writing networking code, big codes, you can simply call this function. Isn't that easier? Yes. Then PVM is parallel virtual machine. This one is older than the message passing interface, and it used to make several computers behave like one large computer, but nowadays this message passing interface is more popular. Then we have remote procedure call, RPC. Remote procedure call is very important. You can imagine you're calling a function called add function. With add function 5,7 is the parameters. The function is inside your own computer, easy in that case. But what if this function is on another computer? Can you still call it? That is the question. Yes, you can. That is using this remote procedure called RPC. Or you can think of it like this. Your computer calls a function, another computer executes it and returns the result. That feels exactly like calling a local function. That is why it is called remote procedure call. We can take an example where you have Google Maps. You ask it to find the shortest route. So how you're asking, either through your phone or laptop, let's say phone. Your phone doesn't calculate it. No, it doesn't. Your Google server does. The phone only simply calls the remote function. That is remote procedure call, RPC. Then you have RMI, which is remote method invocation. This is similar to remote procedure call. What is the difference? In remote procedure call, it calls function. In remote method invocation, it calls objects like in Java. Then you have CORBA. What is CORBA? Common Object Request Broker Architecture. CORBA. Common Object Request Broker Architecture. CORBA actually allows programs written in different languages, let be C or Java, C++, Python, etc. to communicate with each other. Then you have DCOM. DCOM is Distributed Component Object Model. Distributed Component Object Model. This is Microsoft's version of distributed object communication, and it is mostly Windows based. All you have to remember is the MPI, message passing interface, PVM, parallel virtual machine, RPC, remote procedure call, RMI, remote method invocation, CORBA, common object request broker, DCOM, which is distributed component object model. That's libraries and standards. In the next video, we'll be discussing about design issues and challenges. So till then, bye-bye.